Okay guys, chapter 4 starts with inverse functions. So we've talked about how do you determine a function from every input has exactly one output and the vertical line test. But functions also can have a special quality called one-to-one. A one-to-one function is basically not only does every input have one output to be a function, every output also has exactly one input to be one-to-one. If it's one-to-one, it becomes much more easily determined, the inverse of it. We have steps we can do that with the inverse also being a function without any domain restrictions. So to determine if the functions are one-to-one, we're assuming they're already functions. We are looking for the same output to have two different inputs. So because we see a 2,7 and a 3,7, one output with two inputs, two different inputs means not one-to-one. However, if we look at 2, that this is one-to-one. To determine if a function itself is one-to-one, you have two options. We have the equation option. You have to assume f of a equals f of b, and then show that means a equals b. That means if there's two different outputs for two different numbers a and b, those numbers are actually the same number. So what that means is if negative 4a plus 12 in this case equals negative 4b plus 12, so plugging in a and b to the function, I need to get it back to a equals b. So subtract 12, negative 4a equals negative 4b, and divide by negative 4 to get a equals b. That means this thing is one-to-one. If you get anything besides a equals b, it's not one-to-one. Case in point here, if 25 minus a squared equals 25 minus b squared, means subtract 25, negative a squared equals negative b squared, divide by negative 1, a squared equals b squared. And if I take the square root of a squared equals the square root of b squared, really that means a is plus or minus b. Because technically, if we let a be, without loss of generality, it could be b equals plus or minus a. But remember that if a squared was 25 and b squared was 25, it doesn't mean that a was equal to b. One could be 5, one could be negative 5. So because we got something besides exactly a equals b, then this is not one-to-one. So this is generally how you show if a function is one-to-one or not, by using this concept of if you have the same output twice, it means that you had to have the same input for both of those. Now, the easier way for most people to do this is graphically, because graphically, just like the vertical line test can determine if something's a function, we have the horizontal line test, which helps you determine if something is one-to-one. It works exactly like the vertical line test, only, shocker, it's a horizontal line instead of a vertical one. You probably couldn't tell that from the name. So graph the following functions and use the horizontal line test to determine if they are one-to-one. So using some of our skills from chapter 3, negative x plus 3 squared minus 2. This is a downward facing parabola that starts at negative 3, negative 2. But otherwise it doesn't have any stretches or shrinks. Now if I wanted to do the horizontal line test here, I'm like, oh, if I draw a horizontal line anywhere, I hit the function twice, it's not one-to-one. Now what do you notice? If I draw a horizontal line, for example, there, it fails the horizontal line test, so it's not one-to-one. What about f of x equals 3x minus 2? Start at negative 2, slope of up 3 over 1, or down 3 over 1. Now, if I draw a horizontal line anywhere through here, it's only going to hit it one time, which means it passes the horizontal line test, which means it is one-to-one. So generally speaking, how you show a function is one-to-one show f of a equals f of b, so two outputs implies the same input. To show it's not one-to-one, you can take two different input values and just plug them in. So for example, in that 25 minus x squared, you could have plugged in 1 and -1 and said, oh, 124 and -124. Well, there's the same output with two different inputs. That's also an option if you can plug in numbers, if that's what you're good at. You can sketch the graph and use the horizontal line test. And if the function is either strictly increasing or strictly decreasing over the whole domain, it's automatically one-to-one. All that means is if the function never turns around, that there's no way to hit the same y value twice. Now, interesting fact about a function and its inverse. The inverse switches the x and y values from the original, switches the inputs and outputs, which means it also switches the domains and ranges. So when you have something like find the domain and range of the inverse and find a point on the graph, all of that comes from finding this information on the original. So for the original, the domain, what we know about square roots is you can only plug in non-negative numbers underneath it. So the domain here is -3 to infinity. And the range, our outputs are only positive or non-negative. So it's from 0 to infinity. So what happens for your inverse is it takes the domain and switches it to the range. It takes the range and switches it to the domain. Just flips them. For a point on the graph, I can pick any point here. Let's plug in 0. So we have a point. If I plug in 0, you can plug in anything. If you want, you can plug in, actually, let's just plug in 1. 1 plus 3 is 4, the square root of 4 is 2. So we have the point 1, 2. So what does that do for the inverse? Again, the inverse switches the x's and y's, so it takes your two coordinates and it flips them. So even when you don't know what the inverse is, you can still find some information about it based on the original. Here, so we know that the domain is from 0 to infinity, the range is -3 to infinity, and a point on that graph will be 2, 1, because 1, 2 was on the original. Okay, now let's talk about how we can possibly find a function. In the past, when we wanted to determine if two functions were inverses, we did f of g of x to show it was x and g of f of x to show it was x. However, this could be a potentially tedious process, and you can do it again. If you want to recall how to do this, I'm pretty sure it's in 2.8. But otherwise, I want to talk about how to actually find the inverse of a function. So we'll ignore this page for now. Even though this is a good property of inverses, being able to find the inverse itself is a better proper skill. So to find the inverse of a one-to-one function, you change f of x to y, and you switch the x's and y's, and then you have to solve the equation for where y is now and replace it with f inverse of x. So to determine the function is one-to-one, and if so, find the inverse. So this one is f of x equals 2x plus 5. Since 2x plus 5 is constantly increasing because it has a positive slope, it has to be one-to-one. If it's one-to-one, you can find the inverse. If it's not, you can't. So you change your f of x to y, and then you switch the position of x and y. Every coefficient stays in the same place. The only thing that happens is all x's change to y's, all y's change to x's. So x equals 2y plus 5. Your goal is to get y by itself, so subtract 5. Get 2y, I'm going to move it on to the left, is x minus 5, divided by 2. Y equals 1/2 x minus 5/2. Once y is by itself, you replace y with f inverse, because now you've successfully taken the inverse. And this is the function that's the inverse. So it's a much easier process, I think, than using the f of g of x, if you can just find the inverse yourself. The inverse of a linear is going to be a linear. And we'll do more inverses and some of the implications in the next video.